So morning all. Today and on Wednesday we're going to sort of wrap up the business of training neural networks. I'll be covering most of the topics today, and we will have I'll have material to present for maybe half of Wednesday. Instead of stretching it, I'm going to leave the second half of the class on Wednesday, if possible, for questions. I posted a note about this on Piazza. So, is it better? It's too loud. 1, 2, 3. Okay. So if you have any questions, please post these on Piazza. I'll take notes and come back and answer those if I can. Right? So getting on with the topic, what we've seen so far is that, quick recap, when we train a neural network, we define an objective function of this kind. The objective function is based on a number of training instances. And do we have chalk? I'm sure there's chalk somewhere. Give me a second. I have chalk. Thank you. So the way we do it, we define a loss function of this kind, which actually combines the losses of many training instances. So we start off by defining a divergence function, which defines the error between the desired output for a training instance and the actual output that you get from the network. We average this over many training instances, and that is our loss. We will optimize our network parameters. Do you mind shutting your laptop? Do you mind shutting the laptop? You. Yes. So we will optimize our network parameters by minimizing this loss. So this is a total or an average loss over all training instances, which quantifies the difference between the desired output and the actual output of the network as a function of the weights. We find the weights that minimize this loss. So here are all the various components. This is the total loss. This is the desired output in response to an input X. This is the output of the network. This is the desired output. This is the actual output. This is the divergence function. Here's the average. This is the loss. This is what we minimize. And so the way we did it was to use gradient descent. Now, in order to be able to use gradient descent, we need to be able to compute the gradient of this loss function with respect to all of the parameters. And so by the property of the linearity of the gradient of the loss function with respect to the weights is simply the average of the gradients for the individual training instances. So for each training instance, you have a divergence between the actual output of the network and the desired output of the network. You can compute the gradient of this divergence with respect to the parameters. You'd get one such term for every training instance. And we'd average this over all of the training instances to get our total gradient over the entire training set. And once we get this, our minimization algorithm simply uses the standard gradient descent update rule, where we iteratively take steps against the gradient. So you go minus some step size times minus the gradient. And if we keep doing this, we expect that we will actually arrive at some sort of a minimum. And this divergence we saw can be computed using backpropagation. We spent all of 2 classes ago and part of last class on how we would compute this using backpropagation. So there were issues with the whole process. We have issues with backprop and gradient descent. Now, first, we minimize a loss which relates to classification accuracy, but is not actually classification accuracy. And so here, for example, this divergence, we require this divergence to be differentiable. If you're trying to build a classifier, classification accuracy is based on the number of classification errors, so which are counts and are not differentiable. So we come up with a proxy that is differentiable. And minimizing this proxy is not guaranteed to minimize classification error. We saw that. Minimizing the loss is expected to, but not guaranteed to minimize classification error. Secondly, even minimizing the loss is hard enough. And we spent a lot of time on why minimizing the loss is hard. So we are doing gradient descent. Now let's say we have a loss function whose contour plot is something like that. I've drawn a nice kind of convex loss function. Now, if I take slices in this direction, so this is a 3D plot. This is, say, W1. This is, say, W2. And the contours, this would be the innermost contour. You can imagine the contours as showing a height. And so if I took a slice in any direction, in this direction, if I were to plot the function as W1 versus the loss as a function of W1, you'd get something of this kind. And in this direction, if I took a slice, that's going to be W2, and the loss is a function of W2. And what we see is, in the vertical direction, the convexity of the bowl is much less than in the horizontal direction. So this leads to a problem in that if I, there's never anything useful here. So let me make this a little more steep so to actually give you the idea of what's going on, right? So now what happens over here is that if I want to arrive at the optimum quickly from some starting point, I have to take large step sizes on this plot. But if I take a large step size that wide, what will happen over here is that that's going to actually end up being too large. So now I can end up, instead of going down the bowl, I can end up going up the bowl. And as a result, you're going to have behavior of this kind. A step size that makes me arrive at the optimum fast for W1 can end up having the error blow up with respect to W2. So what is the net effect? Although in one direction I'm arriving towards the minimum, in the other direction I'm going away. So overall, I'm not actually arriving at the optimum. Now I can compensate for this by trying to say, okay, in this direction, I will make my step size smaller. But then when I make a step size small in this direction, the step size in this direction also gets small. And now the number of steps I need to take in the broader direction to arrive at the optimum ends up becoming much, much greater. So now convergence slows down to a crawl. This is a standard problem with gradient descent. Now, what happens when we actually use gradient descent for a neural network? How many weights, how many biases do we have? We can have hundreds of thousands, millions of biases, millions of weights. So if you actually plotted this function for each of these, you'd have the loss function. So these would be all the various weights in your network, W1, W3, 2, W3, and so on. And each of them is going to have a different shape of the loss function. And if you're going to take a step size that guarantees convergence in every single direction, then remember, if you diverge in even one direction, you're not arriving at the optimum, and you have millions of parameters to optimize all simultaneously. So if I find the step size that ensures that even in the steepest direction, I actually go towards the optimum and don't diverge, that means I have to focus on the steepest direction. I'm going to take the optimum step size for the smallest optimum step size across all directions. And when I try to diverge, make sure that I get convergence over here, those corresponding step sizes are going to be too small in every other direction. And as a result, your convergence is going to slow down to a crawl. So this we covered in the last class. Everybody remember this? Yes?
The loss with respect to a single weight, is it guaranteed to be convex or
It's no, I'm just drawing convex figures. I mean, we also covered the issue of that the error surface is really not convex. And what we really want to do is start off with large step sizes and converge to a small step size just so that you can escape local minimum. But then the issue here is that a fixed step size for all the weights in the network can result in convergence of one weight while causing divergence of the other weights. And if you try to compensate for this by making sure it converges in all directions, you're going the other way. It's going to become too slow. So one way to try to do this, we saw, was to sort of normalize actually expand it in these directions. Normalize the loss function by sort of rescaling the various dimensions. So if you rescaled all of the various dimensions, then this modified loss function is going to end up having similar eccentricities in each direction, and now a common step size is guaranteed to ensure that you're converging in every single direction. Yes? The loss, no, it depends on both. So we will see this later, maybe in the next class. Your loss function will affect the convexity, and we'll get to that in the next class, right? But so it's a combination of the nature of the problem and the loss function. So we can try to normalize the curvature in all directions, and once you do this, then you can use second order methods like Newton's method, except what happens is the process of normalizing the directions so that it becomes something like this means that at the current location you have to sort of you have to compute the inverse Hessian to figure out how each of the dimensions must be scaled. And if you have 1 million parameters in your network, the Hessian matrix is 1 million cross million. You're not actually going to be computing the inverse of this Hessian anytime soon. So this doesn't work. Now the alternate is to treat each dimension independently. So the reason we are having this problem is that we are using the same step size in every direction. And clearly this is what is causing the problem, right? If I use the same step size for the horizontal direction as the vertical direction, what converges in one direction is going to blow up in the other direction. Someone asked us on Piazza, who was it? Is what somebody in class? Roshan, right? So why can you not simply make the different directions, step sizes in the different directions independent? And there are algorithms which actually do this. We saw this. RProp simply treats each dimension independently. And within each dimension, if you're succeeding in making the heading towards an optimum, then you keep making the step sizes larger and larger. If at any point you overshoot and the error increases, or you think you're going the other way, then you take a step back and decrease the step size. So you get this adjustment of step sizes in each direction, and you can hope to get to the optimum. And this sort of works regardless of the kind of the objective function, which doesn't even have to be convex, but there are issues. And then we saw the other variant of this, which is quick prop, which is like Newton's method, except that this is also applied independently to every dimension. And the difference between Newton's method and here was that the second derivative was computed through differences. So why do we need these crazy things? Why can't we just go off and simply have a different step size in each direction? Does anybody want to take a guess? Why would you not do that?
The convergence is not guaranteed at the same point for all directions.
This has nothing really to do with convergence directly. I wish they had. Let me check. Maybe they have an eraser up there. Give me a second. So the problem is with the figure that I just drew. In the figure that I just drew, the dimensions are independent of one another. So when I get closer to the optimum in this direction, it doesn't affect how far away I am from the optimum in the other direction, right? Because there are two bowls which are orthogonal to one another, which are combining to give me the larger bowl. What happens if the whole thing is tilted? So if I have this kind of objective function, right? And let's say I'm over here. So now what happens here is, if I take a step in one direction, does it affect the distance from the optimum in the other direction? It does it not? So now if I begin looking at the different directions independently of one another, what would happen? One of them says go this way, the other says maybe go a small step this way. But in the process of taking a step here, I may actually end up, I'm drawing this in the wrong place, but I may actually, the direction, the movement in the one direction may in fact flip the direction in which I must travel along the other coordinate. Whereas the correction I'm making in the other coordinate is in the exact opposite direction. And the exact behavior that you will see will depend on the orientation of the loss function of the surface and a number of other factors. What this means is that taking independent steps in each direction can result in effectively unpredictable behavior. Does that make sense to everybody? Right? Yes?
So what if we give a preference order? So instead of taking each dimension independently, what if we kind of make a dependency chain? So only one of the steps we take independently, and then based on that we decide the step of the other direction.
So yes, you can definitely do that. That's you're speaking of doing coordinate descents. And the whole thing is going to become much more expensive in the sense that after each step you're going to have to go through your entire data to decide where you're going in the other direction, right? And that's really not that's not feasible, especially as your training data increases, correct? So yeah, that's a plausible thing to be doing, except you have this other issue, yes?
So if we do PCA first and then doing this in independent direction?
You don't need PCA. That's what multiplying by the Hessian actually does, right? PCA is about statistics. Here you're trying to rotate a function. So when you multiply it by the inverse of the Hessian, you rotate the function so that they are now axis aligned. But how large is that Hessian, right? You're back to the original problem. That's exactly what Newton's method is trying to do. So this is not and so you see why things like rprop and quickprop, which ignore the dependencies between the directions, can lead to somewhat odd behavior. And if you're trying to do simple straight-up gradient descent while ignoring the dependencies between different directions, you see what will happen, right? So now, can we sort of try to consider the joint distribution or the dependency between the two directions, and yet somehow come up with mechanisms that will improve convergence behavior in the sense that they sort of decouple the different directions so that you can get to the optimum faster. Yes, we do these using momentum methods. So the momentum methods are based on a very simple principle. Look at these guys, right? Now, if I have dimensionality independent learning rates, and even assuming that my function is axis aligned, right? So consider what happens. I'm going to plot iteration versus step size for different directions, okay? So the x-axis is the iteration number. The y-axis is the step. So this is iter, and this is step, okay? And this is step for, say, W1. I can do the same thing for W2, okay? So look at what happens for which is W1. So let me call the vertical guy W1, okay? So for the vertical guy, here's what I get. The first one is positive. The next guy is positive. The third guy is positive. The fourth guy is positive. Every single step, if you look at what's happening over here, in the vertical direction, assuming downwards is positive, so I've got my things inverted, but you get the idea, right? So in the vertical direction, it's always traveling in the same direction, right? What happens in the horizontal direction? The first time, it's this way. The second time, it's this way. The third time, it's this way. The fourth time, it's this way, right? So in the horizontal direction, it's bouncing around. It keeps flipping direction. Now, if you just look at these two guys, the fact that one of them is bouncing around and the other is traveling in the same direction gives you an idea, right? And what idea does it give you? It tells you that in this direction, you really don't want to be bouncing around because every step is canceling out what every other step did. In this direction, every step is sort of augmenting what every other step did. So maybe you should be traveling faster in that direction, right? So now this is the basic intuition behind all of these momentum methods. And so the way we will do it is we will keep track of oscillations, emphasize steps in directions that converge smoothly. Which of these two directions is converging smoothly? The one to the right. And we're going to shrink steps in the directions where you're bouncing around, right? So how can we do this? It turns out I can think of every step in terms of the individual components. And at each point, instead of simply taking, so consider iteration number 4 over here. The iteration number 4 is the combination of this positive step and this positive step. So if I were to plot it, you're going to get, positive movement in both directions, right? But instead of just taking this local guy, what I can do is to take an average of all of the steps, all of the gradient steps that have been suggested to me by the gradient, not the steps that I have taken, but the steps that have been suggested to me by the gradient. And if I take the average of everything that happened in the past, how large is this vertical step going to be? Over here. Things are going to be canceling out, right? And so now the net vertical step, for which I will need a different color, is actually going to be something different, right? On the other hand, if I take the average of everything that happened in the past over here, again, these are gradients, not the steps I took, right? If I look at the average of all the gradients in the past, it's suggesting that, this is a good direction. The average is actually going to be longer than the actual step that is currently suggested to me by the gradient. And as a result, now, instead of going this way, I'm going to end up going this way, right? Because the average of these guys is going to be, say, y small, and the average of these guys over here is probably going to be y big. So I've changed the actual step in which direction in which I'm going to be taking a step. Now, which means I have to maintain an average of everything that has been suggested until now. I will maintain a running average, right? And so here's our questions. Yeah.
So we take the step just in the direction of largest gradient and not look at irrespective of other gradients.
No. So in every direction, you're keeping track of all the gradients that have been suggested from the beginning of time until now. And then you're going to take the average of all of these guys for the final step size in that direction. So if you look at what's happening, I have two directions in my figure, right? Here, so this is iteration 0, 1, 2, 3, 4. Iteration 4, this is the length of the gradient in that direction, in W1. But if I take the average of 1, 2, 3, 4, and 5, because they keep oscillating, the net is only going to be y small, right? So both directions are being considered, except that you're not considering just the local value, you're looking at the historical trend. Make sense? Okay. So, yeah.
It's like one second average is the weight of each past step equally weighted, or they are weighted differently?
So the actual method that you use is this autoregressive format, which means that as the further back they are, the less important they get, right? So beta and eta. I should have used a different symbol. They will both be less than 1. And so typically you can think of the correct way to think about this is I'll call the current suggestion, say the step at time k equals eta times the gradient E at time k, right? And then I can say the actual step, S bar equals beta times sk minus 1 bar plus 1 minus beta times sk. So basically what you're doing is that you get the gradient, you're going to get a weighted version of the gradient, which is the actual step size, right? And this is the step you would have taken if you were not maintaining a running average. This is the step you will take. if you're maintaining a running average, which is a linear combination, an affine combination of the step you've already taken and the step that has been suggested, right? This is just a different way of rewriting it. So what this running average does is that in the directions where you have lots of oscillation, this thing is going to get compressed. And in the directions where you have very small oscillations, the length is actually going to get, where it's consistent, the length will actually either stay consistent or even increase. And so the net means that you're going to get converged towards the optimum much faster. So this is the momentum method, where we're calling this the momentum in that the previous step, the step that it's almost as if you continue walking in the direction that you've been walking, and then you change your direction a little bit to account for the gradient. So the overall process is going to look something like this. Here is the original training by gradient descent, where you would initialize everything, then you'd go through all of your training data, compute the average gradient, and then take a step against it. This is the standard gradient descent. If I change this to the momentum method, here's what it's going to look like. I'm going to keep track of the gradient, but then the actual step that I take is going to be a weighted combination of the step at the previous instant, previous iteration, minus the current gradient. And this is what I'm actually going to be using to correct my, adjust my current set of parameters. Here, k is not the iteration number, k is the layer, which is different from what I have over here, just to be, just to clarify, right? So you see the difference between the momentum method and the gradient. Now, here is something that happens. Here's what the momentum method actually does. So let's say you currently took a step in this direction, right? Then you will compute the gradient at the current step, and the gradient is going to point in the direction of the blue line. But then your past step was this guy. So you're going to add a scaled version of the step that you've already taken. And that is going to give you the final update that you're actually going to make in the current step. So this is the entire gradient descent method, right? Now, this is the momentum-based gradient descent method. This is the momentum method. Now, this has an issue. And the issue is that you decide, you look at the gradient at the current position, and then you continue, you add to that some weighted, some scaled version of the step that you have already taken in order to arrive at the final point. And this can be made more optimal by reversing the order of operations. Why? Because I know that I'm going to continue in this direction for a while. That is my momentum, right? The momentum is saying I'm going to continue in the direction that I've already been walking. So the correct thing for me, the more optimal thing for me to do is to continue walking and then figure out where to go and change my direction. So instead of finding the gradient and then adding the step, I can flip the order. I can continue first a little bit and then find the gradient at the current location, and that will give me the subsequent, the sum of the two is going to give me the actual step that I must take. So this is Nesterov's accelerated gradient method. Here's what we do. Observe this equation over here. The new update is going to be a weighted combination of the previous update plus a gradient. The difference between the momentum method and this guy is that the gradient is not computed at the current location, but the gradient is computed at the location that you will arrive at after you take the step. The equation is a little more complicated than the figure. But if you see the figure, you can actually see what's going on. So this, you're first taking a step in the proper direction, computing a gradient at that location, and you're adding, so which is this guy, and then you're adding this gradient to the extended version of the current step to give you the final result. And so how does momentum compare with Nesterov's method? So you can, this example is adapted from something Hinton had online. But I have the colored chart over here showing you Nesterov's method, and the blue one showing you the standard momentum method. Both of them are going to be much faster than simple gradient descent. So here's what over here, the gradient is always orthogonal to the equal value contour. So if you took the gradient at this point, which is this blue, and then added a scaled version of the current step, so your first step was this black arrow, you took a gradient and then added a scaled version of the current step, you would end up at this location. Then you take a gradient at this location, which goes downwards, but then you add a scaled version of this guy that ends up taking you there. So that is the momentum method. In 2 steps, you're going to go where the second dotted blue arrow takes you. On the other hand, Nesterov's method, here's what you would do. You would first continue walking in the same direction, then compute the gradient, and that's going to be the final position. And then in the next iteration, you continue walking in the same direction as the previous green, and then look at the gradient, and that's going to be the final position. So yeah.
Is there a chance that normal momentum will be faster than Nesterov's?
Nesterov's method is provably optimal under various conditions. So there's a very nice paper. I wish I could explain this, except the last I checked, the very first line in the paper says something like obviously, and makes a statement, and it took me half a day to convince myself that it was obvious. So, anyway, so this converges much faster, right? So here's how training with Nesterov would look like. You would first update the weights to continue walking, to take an additional step in the current direction. Then you would compute the gradient in the current position, which is where you got to after taking the step. And then you're going to adjust the position using the gradient after the extension. And you also compute in the process how much you've actually traveled in that current iteration. So you change the order of operations. Yes.
I'm not convinced here, like why it would be faster as compared to.
So there are 2 answers to this. One is mathematically you can show that it is. That was Nesterov's paper, right? But intuitively, what happens is if I take a gradient at the current point, the gradient is sort of going towards the optimum, right? But then if I continue the previous step, I'm going away from the optimum. So I'm adding a suboptimal step to a supposedly optimal step in pure gradient descent terms. Here, I'm first taking the step and then moving towards the optimum. So if the last thing I do is moving towards the optimum, I'm much more likely to get closer to the optimum point than if the first thing I do is to move towards the optimum and the next thing I do is to move away. Right? That makes sense to you? Yeah. So we'll return to this topic of momentum methods in a bit. Yes, David?
There's a question from Piazza. How does momentum resolve the problem with R-graph that it assumes the dimensions to be orthogonal?
So momentum does not resolve the assumption that the dimensions are orthogonal. So what momentum does is there's no assumption at all that the dimensions are orthogonal over here. By just maintaining the momentum, you're always still following the gradient, which means you're looking at the overall gradient. But by maintaining a running average, you're sort of accounting for the fact that in some directions the gradient tends to oscillate, in the others it doesn't. You want to move. You want to be parsimonious in your movement. And what happens if I follow these is that every step is going to be fairly long, and I'm going to have to travel a lot. Whereas by taking the average, you're accounting for trends. But it doesn't make any assumption about the nature of the loss function itself. Okay, let's continue on, right? So the story so far, gradient descent can miss obvious answers. But we saw in the last class that this could be a good thing because in the early iterations, it might actually help you escape local optima. Vanilla gradient descent may be too slow or unstable due to the differences between the dimensions. Second order methods can normalize the variation across dimensions, but are complex. If you're going to invert things using a Hessian, that becomes complicated. Adaptive or decaying learning rates can improve convergence. We saw that in the last class. Methods that decouple the dimensions can improve convergence. But again, all of these tend to be suboptimal or complicated in one way or the other. So the ones that we actually looked at, which you probably which are probably the ones you're actually implementing in your homeworks, are momentum-based methods which emphasize directions of steady improvement and de-emphasize directions where things oscillate. And these are demonstrably superior to other methods, yes.
Could you
vanilla gradient descent refers to?
Where I'm not using any augmentation. I'm just doing, at each step, I'm just taking a single step against the gradient. The basic gradient descent that we had spoken about a couple of classes ago, right? So moving on, rest of the topics for the day. We're going to look at incremental updates. We're going to revisit trend algorithms and generalization. And these are topics for the next class, right? So let's go back and look at incremental updates. Now, what happens when I actually try to train my network? When I train my network, remember, we are trying to learn a function. So the function may be something like the one that's shown by the dotted blue line. But we don't have the entire function. Instead, we have input-output relationships at a number of training points. And we are going to try to use just these training points to learn the entire function. So what we will do is to start off with an initial estimate of all of your parameters. Remember, we are speaking of iterative updates. So we'll start off with an initial estimate for all of your parameters. The initial estimate may give you a function like the curve shown in the red dotted line. And so what we are going to try to do is to adjust our parameters such that this function gets closer to the desired function. And what we have here is that the initial estimate is underestimating the function over here and here. It's overestimating the function over here. It's underestimating the function over here, right? So these are, in this case, the 5 training points. So at 5 training points, the behaviors are different. The way we define the loss was defined over the entire training data. So we're going to try to correct the value of the function at every single training instance, which means we're going to try to push up the value of the function at these 2 points. We're going to try to push down the value of the function at these 2 points. And then we're going to try to push up the value of the function at this point, right? So, and when you do that, then maybe the function, your adjustment maybe pushes the function up over here, pushes it down over here, pushes it up over here, you're closer to the function that you want, but then you're going to repeat the process. Once again, it's underestimating here, it's overestimating at these points, it's underestimating over here, so you're going to have to push these guys up, push those down, push these up, and then you will get new updated parameters which will give you a new estimate, right? This is the overall process of gradient descent. And we'd keep doing this till we got as close as we could for the function. The problem over here is that we are trying in each step to adjust the value of the function at the location of every training instance. So here in this figure, I have 5 training instances. I'm simultaneously trying to correct the value of I'm trying to adjust my parameters so that I'm simultaneously correcting the value of the function represented by the network at every one of these points. So which is to say all 5 of these points. This is what we call a batch update. But then, so think of it this way. I have some function and maybe I have some folded, I have a handkerchief sort of dumped on it, which is trying to mold to the shape. So maybe my function's a bowl and I have a handkerchief, I'm trying to mold it to the shape. Now, you have a bunch of anchors, these are your training instances, you're grabbing hold of all of these and you're trying to adjust this so that the handkerchief eventually conforms to the shape that you want to. And you need a great many hands and a great many fingers to grapple with this kerchief of yours everywhere. There's an alternate way of doing it. And the way you would do it is instead of trying to simultaneously fix everything, you could go around and do this at each of the points individually. You push one position down. So when you push the function down, at that location, the model function is going to get closer to what you want. But this is going to change the value at other locations, right? So because you don't want it to change too much at other locations, you just change it, push it down a little bit. Then you go to some other point and adjust that a little bit. At each point, you want to make these adjustments small enough so that how much it changes at the other locations is not particularly gross. Basically, instead of trying to adjust everything all at once, you sort of adjust each of these points one at a time through small adjustments. And if you have 10 training instances, you would have made 10 steps. But what will happen is that in the process of making 10 individual corrections, at the end, when you've gone through all of the training points, you'd have adjusted the entire function because you'd have adjusted the location, the value of the function at every location in your training set. And when you do that, you can hope to actually have a greater overall adjustment than if you just made a single batch update where you grabbed the whole thing and made one big shift. So this is the technique that we have been kind of following on our homeworks. It's what we call stochastic gradient descent. Yes? This is not the loss function. This is the function that the network is trying to model. Right? So just going back, I'm using an earlier figure. The dotted line is the function that I would like to learn. And the red is the function that I've actually learned. Right? So now, so here's how we are actually going to do it. Minimizing the divergence is going to sort of make the adjustment at different points. Right? So now, when we go through all of our training instances, after each training instance, you're going to compute the derivative at that training instance. And then you're going to make an adjustment to the parameters using that derivative. So you're not waiting to process all of your data. After each instance has been processed, you're going to make corrections. Right? Now, this is what we call stochastic gradient descent. Now, why is it called stochastic gradient descent? There's a caveat in how you actually implement it. So let's say you're trying to model this, for trying to find the dotted line, which is your function that you want, and you have 8 training points. So you have 4 points to the left and 4 points to the right. So if I sequentially go through the first 4 points, and then I sequentially go through the next 4 points, and then I go back and sequentially go through the first 4 points, and then I sequentially go back through the next 4 points, what will happen? When I go through the first 4 points, it's going to push the function down at these locations. If my network is sort of representing a curved function, then it will naturally sort of push the function up at the other side. Then I go to the next side. Over there, I go and push the function down at that point. What will happen? It pushes the function down over there, but then it sort of pushes the function up over here. And the reason for this behavior is that and then the next time around, I'm going to come back to the beginning and push the stuff down on this side, and it's going to go up on the other side. So if I go through all of the points in a very deterministic manner, I can end up getting such cyclic behavior. If there's any kind of structure to how the data are arranged, I push the data function down here, it goes up there, I go and correct for that, this goes bad, I'm going to keep oscillating between the two. How would you actually want to operate on this kind of data? When you want to operate on this kind of data, you want to push one down on the right-hand side, then you want to go to the left-hand side and push a little bit down, then you want to go to the right-hand side and make an adjustment, then you want to go to the left-hand side and make an adjustment. And if you do this carefully enough, then you're going to end up with a balance function which most closely approximates the horizontal line that you want. So what you want to do is to do something like this. Push it down here, maybe it goes up, changes to that, then you observe that you're now not pushing it down from the right-hand side, you're pushing it up, at least in my figure. And so by making small steps alternately between the two clumps, you can expect to end up with a solution, with an actual solution, as opposed to simply going through the data deterministically. Now, in this figure, I have things very nicely arranged. 4 points to the left-hand side, 4 points to the right-hand side. In real life, you have no idea where the data are. You're looking at high-dimensional data. The functions are arbitrarily complex. So the way you would actually have to deal with this is to randomly go through your data when you perform your stochastic gradient updates. So when you pick up individual instances to make corrections, you must pick up those individual instances in random order for this to work. So so here is the story so far. Actually, I should have I'm missing a slide. Okay, we'll get back to that. So here is the story so far. In any gradient descent optimization problem, presenting training instances incrementally can be more effective than presenting them all at once, provided the training instances are presented in random order. And because they are being presented in random order, This is why we will call it stochastic gradient descent. Exactly how this is implemented, the pseudocode is a few slides down. And this is for generic optimization of any function, so it clearly also holds for neural networks, right? Now, why does this process of incremental updates work? Why can the process of incremental updates actually be more efficient than working with batches? So we'll spend a little time looking at this, and under what conditions do you expect this thing to work, and what kind of behavior can you expect in terms of convergence, how fast you will get the optimum. So let's look at the why first. And for the why, I'm going to look at a very simplistic explanation that's often given using a very extreme example. So let's go back and look at what happens when you're actually performing batch gradient descent. When you're performing batch gradient descent, which is to say you're computing the average gradient over all of your training data, then you have many training instances. You're computing the gradient with respect to every one of the training instances, and then you're taking the average. So this function over here is showing the equal contours of the total loss E, which is over all of the training instances. But if you look at this function for any individual training instance, it's going to be different. This is just the average over all of the training instances. So if you look at the gradients for the individual training instances, they're going to point in different directions, as shown by these little blue arrows over here. And what we do is to compute the average of all of these lines. And the average is going to give you this red arrow, which is the average gradient, and then your optimization is going to take a step in the direction of that average gradient. So if you look at the function over here, all of these blue lines show the different directions, the gradients for the individual instances, and the red line sort of illustrates the average that you get, and that is the direction in which you would move, right? But let me take an extreme example. All of my training points are at the same location. If all of my training points are at the same location, what happens? Then every one of these guys is giving you the same gradient. The average is going to be the same as the gradient with respect to any individual instance. Correct? So what will happen is that after having processed all of these guys, I have T training instances. I've processed all of those guys. I've gone through T training instances, computed T gradients, taken their average. At the end of it all, I got exactly the same effect as if I had had only one training instance, because the average of all T of them is the same as the gradient for one training instance, right? On the other hand, if I make an update after every individual instance, what happens? Each of them is going to sort of make an adjustment. I'm going to get a much greater overall correction, even if my individual step sizes are smaller. And so if I make incremental corrections after every individual training instance, I can expect to get much closer to the function at that point than if I take an average over all training instances and then make a correction, because if all the training points are identical, the average is the same as just using only one instance, right? And they don't even have to be all the same. They can all be very close to one another, and you get exactly the same kind of behavior, right? So as the data get increasingly diverse, the benefits of incremental update can be thought of as decreasing. When the data are completely random, that's when you're going to get potentially the worst behavior from incremental updates. And even in that case, as we will see, you can actually end up getting a benefit overall from simply doing batch updates, right? So, yeah.
May I ask, in the feature we saw a function. May I ask, this is the loss function?
No, this is always, everywhere in these cases, I'm trying to plot the function that you're trying to model,
I see.
right? So remember, the neural network is in all of these examples, and this is not a loss function. So over here, I'm going to be using these figures again, so it's worth looking at it. When I plot a function of this kind, this blue dot over here is the function that the neural network is trying to model. The red curve is the function that it currently models using the current estimate of the weights.
Yeah. Then I think, given different data set,
Mm-hmm.
will we have different desired function?
No, the desired function is the underlying true function, correct? What the data set really does. So ideally, we want to model the function everywhere. In practice, we cannot, because you don't know the value of the function everywhere. You only know the value of the function at the training instances. And so we are sort of trying to fit the function at the locations of these training instances and hoping that it fits everywhere. Okay. We discussed, right? We'll actually spend some time looking at the implication of this assumption in just a few minutes, right? Any other questions?
Yeah, so if we are training in many smaller batches, is it equivalent to having more chances of updating given the same size of data?
Yes.
And I think if it is in this case, it is the same as just kind of scaling the steps of the results if we train in a whole batch of data. Why not just scale it?
Okay, just wait for a few minutes and ask this question after 20 minutes. Okay? If it's not been answered. All right? So we sort of get the intuition behind what we are doing over here, right? But let's get beyond intuition. How well does it actually work? This is to answer your question. 30 minutes? Thank you. So here is how the stochastic gradient update actually works. This is the pseudocode. You're going to initialize all your parameters, then observe that within each iteration, the first thing you do is to randomly permute all of your training instances. And the reason you randomly permute all of your training instances is that you want to go through the training instances in different order and different iterations, right? And then subsequently, after each instance, you're going to be making an update. Now here, I've also made a second notation. The step size that I have used is now got a subscript where the step size is actually a function of the iteration, and we will see why that is an issue, right? So to see why that's an issue, let's go back and try to look at how our functions behave. Now, let's say these black dots are all of my training instances. And let's say, for simplicity's sake, the nature of the function that I have used to try to model these dots, the input-output relation of these dots is a straight line. So in that case, the best case straight line is going to be this red line, right? Note that even in the case of a perfect fit, you're not actually correctly modeling any single training instance, because your best fit depends on the nature of the function that you're able to model, right? So now if I begin going through this and I begin incrementally correcting this line for every training instance, right? Then I would go here, push this line up, go here, push this line up, go there, push the line up. I'm going to keep continuously adjusting for the individual training instances. Will this ever converge and actually give me the line? Not really, right? Because at each point, I'm looking at one training instance, and this is not correct for any single training instance. So as far as individual training instances are concerned, the function is always wrong. So anytime I consider a single training instance and adjust for it, there will be an adjustment to make, and the function will change. So what this means is that these updates will never converge to anything useful. So what we want to do is to shrink the learning rate with iterations to prevent this. In other words, in the beginning, for every individual training instance, I'm going to make a correction. But the corrections I make are going to get smaller and smaller and smaller with time, because if they didn't, then this process will never converge. The thing is going to keep bouncing around, always following the latest training instance. Clear to everybody? Right. So what is the nature of the constraint on the step size to ensure that you can actually find the optimum, that you can actually estimate the function properly? One thing is obvious. You want the step sizes to shrink with iterations. After you've been training for days and days and days, if the function is still bouncing around, something is wrong. So literally this means that as you keep processing your data, as you progress through your iterations, the size of the correction you make must keep decreasing with the iterations, so that in the limit, when you're close to the optimum function, you're not going to change it by any significant amount simply because it was off for one single training instance, right? So you want the step sizes to decrease. But is that all? There's something complete, there's a second criterion that you want to actually be able to, if you start off from somewhere that's very far from the optimum, you still want to be able to arrive at the optimum, right? This means the step sizes cumulatively must still be able to span the space of parameters, right? So these two can be, so this is first encapsulated in this idea over here. You want a step size that reduces with iterations, right? And secondly, how does it actually reduce? Let's take a look. But before that, a little bit of terminology. I should reorder my slides. The iterations, as we see, can make multiple passes over the data, right? I'm going to call each pass over the data an epoch. So an epoch over t, a training set with t samples, is going to result in t updates. So observe that each time I go over the entire training set, for each training instance, I'm going to make an update. So when I go over t training samples, I'm going to make t updates. This is something for you to keep track of, right? So now, here are the properties I want for my step sizes. I want my individual step sizes to be such that if I start off completely wrong, I can still get to the correct solution. This means that the step sizes must sum to infinity, or at least to a very large number. The step sizes should be should be such that over the duration of a training, no matter where I start from and no matter where the optimum is, I should be able to get from my starting point to the optimum, right? At the same time, I want my step sizes to converge. So for that, I have the second criterion, which is to say that the sum of the squared step sizes must be finite. I want the sum of the step sizes to be infinite. I want it to be able to sum when I'm summing over the entire infinite sequence, so that I can span the entire space. I can search the entire space. At the same time, the step sizes must converge so that in the limit, the individual step sizes are very tiny and don't really make a big difference. So I want the sum of the squared step sizes to be finite. These are the two criteria my step sizes must satisfy for the entire process to work. So you guys who had questions about when and why and how we do this, does that answer your questions? Right? So now what is the fastest? This is a series, right? What is the fastest series that sums to infinity and yet is square integrable? This is just the harmonic series, 1 over k, right? The sum of 1 over k, what is it? Sum of 1 over k is infinite, right? It's a non-convergent series. But the sum of 1 over k squared is definitely finite. So an optimal step size, this is a very great step size, where the step size is literally 1 over k. More generally, we sort of, you never really run infinite steps in the first place, right? So you don't have to follow these very rigidly, but nevertheless, having a step size schedule that satisfies these parameters kind of makes sense, and which is actually what we will do, as we will see. So more generally, we're going to use heuristically determined step sizes, and here is what happens. If the loss is convex, stochastic gradient descent will converge to the optimal solution. If the loss is non-convex, it's going to converge to a local minimum if you've got all kinds of ugly functions, right? And here's how it's going to converge. Now, we sort of looked at the notion of convergence in at least in the slides from the previous class. You're going to define convergence in terms of the difference between the value of the function at the current step and the value of the function at the optimal step, optimal location. So this difference is going to be some criterion for convergence. Now, there are a couple of different ways to look at this. When you have, let's say this is the optimal location, and this has and the function has some value over here. Your iterations are going to sort of trying to go towards this guy, And they may not uniformly go towards this guy, but the idea is to try to get towards this. So there are a couple of different ways of quantifying how far you are from the optimum. One is to say, what is the distance of my current location from the optimum? And so if I look at two subsequent steps, the two distances are going to be different. And if you're doing a good job, then in the second step, the distance must be smaller than in the first step, right? The other way of looking at it is to say, if I draw an epsilon ball around the current point where the radius is, say, epsilon, how many steps does it take to get into this ball? The fewer the number of steps it takes to get into the ball, the faster the algorithm is converging, right? So both of these. So this is we looked at this first definition in the previous class, or at least it's on the slides. I didn't actually go over it. But here, let's look at it in terms of this epsilon ball definition. How many steps does it take to actually get within an epsilon ball? Now, for strongly convex functions, things that look kind of quadratic, then if you use stochastic gradient descent, then the number of steps that it takes to get into any given epsilon ball is of the order of 1 over epsilon. As you can see, if epsilon gets smaller, that number gets larger because you need more steps to get into the ball, right? If the function is if you think of it this way, in k steps, you're going to be 1 over k closer to the optimum than you were at the beginning. If the function is convex but not strongly convex, that actually changes. That convergence rate, instead of going from 1 over k, it becomes 1 over square root of k, which means you're getting there much, 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 much slower, right? And so this is not a very great convergence because, as we saw in the last class, when I use batch updates, the convergence is much faster. Over here, the time taken is, even for strongly convex function, is order of 1 over e. Whereas for batch updates, it's order of log of 1 over e. That's so much faster, right? So the batch updates are expected to can be expected to converge in far fewer iterations. The problem really lies in the definition of an iteration. In a batch update, in a single iteration, you're going to process all of your training data. So if you have t training instances, you're going to process all t training data. In an incremental update, in a stochastic gradient descent, you're going to process only one training instance, any individual step. So when you go through in a single pass through the entire training data, all the individual steps are quite small. You're cumulatively are going to make a much larger step overall. And so SGD performs t updates for every batch update, but batch gradients actually converge faster. If you trade the one off for the other for sufficiently large training data, you're going to find that SGD is actually going to be better than your batch updates. It also comes with other advantages like being able to perform computations in parallel, but let's get to that later. So, but here's an example of how things actually converge on a very simple problem. This is k-means. We're not talking about neural networks. We're talking about k-means. So this green curve is how the algorithm converges in terms of the squared loss, which is what you use for k-means, if you will remember, when you're performing batch updates. And you can see that after even one iteration, the error is actually going to be slower than when you're doing stochastic gradient descent. But then you see these bars. What do these bars mean? So on this data, I can start with these clusters and use different sets of training instances. Each training instance is going to end up with a different error, a different convergence, right? And so these bars show you the range of loss values at a particular iteration over different training instances. And you can see that these bars are actually quite small for k-means. Now what happens when I use stochastic gradient descent? Stochastic gradient descent, observe that the whole thing, the function actually comes down much faster, but it doesn't quite arrive at the loss that this guy arrives at, number one. But number two, look at these bars. Across different runs, the variation can be quite large, right? So why exactly is this? Now, first, let's try to understand the notion of the variance. And for that, let's go back to this figure that we've seen several times. When I have a neural network, and I'm trying to use the neural network to model a particular function, what am I actually trying to do? I'm trying to find the parameters of the network such that the expected divergence between the actual output of the network and the function that I want to estimate is minimized, right? So this is the expected divergence, which is simply the integral weight of the divergence weighted by the probability over the entire space. We can't actually compute the expected divergence, so what we will do instead is to take the average divergence over many independently drawn training instances, right? Now what happens? What I really want to estimate is this guy. So what I really want to minimize is the expectation of the divergence between the function at the value of x and the desired output of the value of x. This is basically what I want to minimize, correct? What I am minimizing is 1 over n summation I, the divergence of function at xi, comma, the desired value at xi, right? Now, this is my error. So I want this guy, or this is my loss, right? This is what I want to minimize. This is what I'm minimizing. The two are not the same. But then let's look at the expectation of the loss. The expectation of the loss is simply going to be, because the expectation goes inside, 1 over n summation over I, expectation of the divergence of f of xi d of xi, right? And the expectation doesn't really depend on the specific sample. I'm treating the samples as a random value. So this is going to be 1 over n times the expected value of the divergence. I'm not right, and the n's cancel out. So this means that the expected value of the loss is the true loss, is the actual loss that I'm trying to minimize. All is fine, right? What about the variance of the loss? So everybody get what I'm doing over here, right? This is easy. Now what happens when I have the variance of the loss? If I consider the variance of the loss, I'm looking at the variance of 1 over n summation I divergence of, I'm just using a shorthand notation, right? If I think of all of my independent instances as statistically, of all of my training instances as statistically independent, that's going to be 1 over n squared times summation n variance of divergence, which is going to be the variance of the divergence over n. So what exactly do I mean by the variance of the divergence? If I take individual training instances, if I draw individual samples from my data and compute its divergence, then over all of my training data, over my entire space, I'm going to get lots and lots of values of divergence. I can compute the variance of that, right? And the variance of the loss for a batch of instances is going to be 1 over n times that much, right? So the n is the size of the batch. Now let's hang on to this thought. Now the empirical error is an unbiased estimate, as we saw, of the expected error, although there's no guarantee that minimizing the empirical error is actually going to minimize the expected error. Secondly, the variance of the empirical error is going to be 1 over n times the variance of the divergence itself. So the larger the variance, the greater the likelihood that the parameters you estimate to minimize the empirical error will differ significantly from the parameters that are required to minimize the true error. Now let's try to understand this pictorially, right? So before I do that, so what happens when I consider stochastic gradient descent? In stochastic gradient descent, at each iteration, SGD focuses on the divergence of a single sample. So the loss that SGD is minimizing at each iteration is simply going to be a single divergence, right? Divergence of a single sample. What is the expected value of this loss? The expected value of this loss is simply the expected value of the divergence. So the loss that SGD minimizes, 10 minutes, yeah, is also an unbiased estimate of the true loss. But what about the variance? The variance, now this n is size 1 for stochastic gradient descent because you're minimizing the error for one instance at a time. So the variance of the loss that you're minimizing when you use stochastic gradient descent is going to be the variance of the divergence itself. So when you compare the batch versus the SGD, there's a factor of n difference in the variance of the loss. Now all of this is math, right? Let's try to understand this with real figures. So let's say the blue line is the function that my network is trying to estimate, trying to model. Using the current estimate of the parameters, the curve that I get is the red line, the red curve. So there's a gap between the blue and the red, right? And this gap has some area. And what my training tries to do is to adjust the parameters to minimize this area. But then, for that I need the entire area. You don't actually have the entire area. For the entire area, you need the entire function. Instead, what we will do is to draw some samples, and then we're going to try to find the difference over here, and you're going to try to minimize the average length of these lines. And if you minimize the average length of these lines, you hope that the red curve is going to get closer to the blue curve. That's what training really does. But then here is the problem, right? The average length of these lines that I get is going to change with the training set I choose. So here I have some average length. This guy says that the curve must go up here, it must go up here, but it must go down in these two regions, right? If I had a different set of training samples, these guys, then this guy is going to tell me that the curve must go up everywhere. I'm completely missing the point that there are some locations where I'm underestimating, right? Or overestimating. So depending on the specific set of training instances that I get, I'm going to end up with different behaviors. So by changing my training set, the function that I learn is going to change a whole lot. This is what I mean by saying that you have a variance in your estimate. And the variance depends on the specific set of the specific training set that you choose. So how can you minimize this variance? To minimize this variance, I have lots of training samples. The more training samples I have, the more that average is actually going to be indicative of how far off I am. And so this will actually help me, right? Now the problem with SGD is I'm using only one sample, and depending on where the sample lies, I can end up with completely different guesses as to what I must do to the function. Out there, it looks like my function is just fine. Out here, it says my function must go up. Out here, it says my function must go down, right? Or is it the other way, right? It must go down. So depending on the specific location where I end up with my sample, I'm going to end up with completely different guessed behaviors for my training. And so the variance is going to be very, very large, right? So this is what we mean by saying variance. These variances are large, which is why these bars are very large for SGD, but they're quite small for batch updates. I'm going to go a few minutes over. I just want to close this topic up. So SGD uses the gradient from only one sample, so it's consequently high variance, but also provides significantly quicker updates than a batch. So is there a good medium? Here's what we can do. Instead of just taking one sample at a time, I can take small subsets of samples at a time. If I take subsets of samples at a time, I'm going to adjust the function at a small randomly chosen subset of points, but I'm going to keep my adjustment small as before. As before, I'm going to vary the subsets randomly in different passes through the data. This is what we call our mini batch update. And when you do this, here's what happens. Instead of updating things one step at a time, I'm actually going to be updating one batch at a time, where I compute the average gradient over the batch and then make the updates, right? So basically at each point, I'm going to be taking some random subset of my training instances, computing the average divergence over those guys, and that's what I'll be minimizing. And here's the nice bit. So this is the batch error over the mini batch. The expected value of the batch error is also the expected divergence. So the batch error is also an unbiased estimate of the true loss. So we are good. The variance of the batch error is going to be 1 over b times the variance of the divergence. And 1 over b is the batch size. So as you can see, because 1 over b falls really fast, having a single sample at a time versus having 10 samples at a time, you're going to get 1/10 the error, 1/10 the variance, right? And so this actually will give you a much more stable estimate while giving you some of the benefits of stochastic gradient descent. Now that's not entirely true. So if you actually go through the math, here's what happens. For mini batch updates with the batches of size b, the convergence rate is 1 over square root of bk. So this looks like it's actually converging faster because the batch is larger, right? But then in any given input, in any given size of training set, I'm going to get 1 over b fewer updates because I'm batching my data in sets of b. So when you take that into account, you actually end up with a degradation of square root of b in terms of convergence rate with respect to stochastic gradient descent, which is kind of nutty, right? However, in practice, the objectives tend to be not convex. So mini batches actually with appropriate learning rates end up being much more effective, and you also get the additional benefits of using matrix libraries and such like. And so here's what the behavior looks like when you use mini batches. This is with batch update, this is with stochastic gradient, and this is for the same k-means problem with mini batches, and you can see that it actually converges much faster than the batch update to actually a much lower error than SGD itself does. And this is what you guys are doing in your training, right? So last topic, last issue, whenever we are speaking of error, we are really speaking of the overall training error after each iteration. But then how do you compute it? You can't really, right? I can't make an update and then go through my entire training data just to compute the error. So if you want to actually validate any of these ideas, you have no way of doing so because you're never actually going to process your entire training data after each update to compute the error. Instead, you will typically estimate it based on some held out set or using some running estimate, right? So stop on these two slides. In training is usually performed using mini batches. The mini batch size is a hyperparameter to be optimized. The convergence depends on learning rate. And so remember that we found that we saw that 1 over k is a good learning rate because it falls off like that. But we also can do something like this where you hold a learning rate till things converge, then shrink it, then hold the next learning rate till things converge and shrink it, and that too satisfies the desired properties that the learning rate sums to infinity and it's square integrable. So this is something that is more common. And in advanced methods, we use more adaptive updates where the learning rate itself is determined as part of the estimation. We will see this in the next class. So here is the final slide. SGD, presenting training instances one at a time, can be more effective than full batch. For SGD to converge, the learning rate must shrink rapidly with iterations. SGD estimates can have higher variance than batch estimates, but mini batch updates operate on batches of instances at a time and can actually give you the benefits of both the batch update and the SGD. They have lower variance than SGD. The convergence rate is theoretically worse than SGD, but in practice, because you're able to perform batch processing, things tend to be much faster. In practice, also because your loss functions are fairly complex, it turns out that this thing tends to be more robust and give you good estimates. I'll stop here. Any questions if you have time for it? Yes.
How do you optimize the batch size?
That, unfortunately, there's no magic number for it. This is something that you have to determine empirically. Typical numbers, people have arrived at for different problems, people have arrived at various numbers after experimentation. I think 100 is the standard size that you tend to use, right? Yeah.
From the figure before, I mean, it seems that the SGD reaches the lower loss one, lower loss than the.
No, this is SGD. The red one is the SGD.
Yeah. SGD is much lower.
So SGD actually has a much.
The whole batch is much lower.
So this is the training data on the entire batch.
The green
The green one is batch.
Yeah.
Batch is much lower.
So maybe we could first use SGD and then use batch minimization.
So again, no, but observe that blue is mini batch, and this gets the same same error as the green.
Not same, but a little bit higher, right?
That's minuscule. It's really, if you run, again, you have this error bar, right? If you look at the error bar, so in practice, it's not a big deal, right? This tends to be the best compromise. Yes.
What if we increase the step size for batch?
Pardon me?
Instead of average, we take like a bigger step in batch grading.
So that's a scaling constant. It really shouldn't matter, right? The point is, eventually, you still want these properties, the square integrability and the summation to infinity to hold. Thank you. We'll complete this in the next class.